we did on Friday, we're going to work with more volumes of revolution. But we're going to call this using the washer method. And the key on this is we're still integrating area from A to B to generate volume. But this time when we slice these figures, what we're going to have is we're always going to have some kind of a hole right in the middle. So we're always going to have these shapes like this, and what we're going to have is we're going to have the only solid part of this is this part right here. So this is the only solid part. All of this around here, and so, if I filled this all the way in, I don't know that I get a chance to fill it all the way in. But this blue part that I'm shading is the solid part of these, what I would call a washer or a disc, or kind of like a donut shape. And the key is you have two radii. You have a little radius, we'll call that r, little r, and then you have a big radius, we'll call that capital R. And the key on this is when you have this, we could find the area of the blue. One second. Sorry, I'll try to cut that little spot out of the tape. If I don't, then you're just going to have to wait for a second. So when we find the area of the blue, we would take pi times the big radius squared minus pi times the little radius squared. And that's the kind of thing we're going to do with this. We're going to revolve these regions, and there's going to be a hole within them. So take a look at this example right here. Let R be the region enclosed by the function, this cubic function that goes up like this, and g of x equaling 2x. So going this line right here, and we're going to revolve it around this line y equals 5. So right up here, we're revolving it around the line y equals 5. When you think about like what that looks like when you actually revolve it, it would take on some kind of a shape. It would kind of look like this. There'd be a hole down here. Do my best to draw this. And, then the inside of it goes like this. Something along those lines. And so then if you spun it around the axes, the only solid part would be this part up here and this part down here, and the rest would be just a big hole. But when you slice this, you'd get a thin washer, thin like that. If you sliced them, if I took and sliced it, or if I cut that thing right down there, you would generate that, and this part right here would be blue in here. This part right here. So what we got to do is we got to come up with these radii. Well, when you think about what this thing looks like, is you got to keep the idea of the distance between two curves is the top curve minus the bottom curve. In this case, here's our axis of revolution, right? This right there is our axis of revolution, y equals 5. And then we got this curve right here, got that line, and then we got the curve that meets right there. So that's our region that we have. Now if you think about those radii, the little radius is the distance to there. That distance right there represents the little radius. The big radius is the distance all the way down to that curve. So you got this, you got A, which is 0, and you got B over here, which you would have to find using a calculator. It looks like it's around 1.5. I don't know if it really is. I mean, I could solve those two and calculate B, but you could use your calculator to calculate B. But in the end, when I'm thinking about how this goes about, we got to go, okay, the volume of this is equal to the integral from 0 to whatever that b value is of pi times the big radius. Well, let's talk about what that big radius is. That big radius is the top curve, 5, minus the bottom curve, x cubed. So if we do 5 minus x cubed, and then we square it, minus, now I got to do the little radius. The little radius is 5 minus 2x. Top curve, which is 5, minus bottom curve, which is 2x. So we do pi times 5 minus 2x. And then we're going to square that because it's pi times r squared, and then that's what we would calculate. Let me show you the solution for it. And the intersection is right there. So that's what I did, only they pulled out the pi, so it's 1.4142. That's like the square root of 2. Anyway, what you have is, take a look at this. If you look at the way the slider builds this, see how those are circular. When we get to here, we create these circles, we create these discs, that there is a hole right in the middle, and there's a hole all the way down to the end. And so that's how we would calculate it, because if we sliced one of those circles out of there, it would be pi times the radius squared minus pi times the radius squared. Okay, let me show you one more example. See if we can come up with a new example. So let's take something like, let's get a different line. Let's take something like this. Now this one's, the line that we're going to revolve around is down here. So this one's kind of like a, if I were to do a drawing of this, it might look like something like this, where you got this here, this graph kind of comes out and comes up here, and then you got a big hole here. This graph kind of comes out like this, and pretend those are sort of symmetrical, but that's the idea that it would be. And this line right here that's going down here, that's the line y equals -1. So when we spin this thing around this rotation, we get this, the green shaded area is this green shaded area and this green shaded area. So when we're going through and calculating this, we're going to have to come up with these radii. You got this thing that kind of goes like, you got this line that goes like this, and you got a curve that goes like this. That's above the x-axis, but then we're revolving it around this line down here. y equals -1. And again, to find the distance between two curves, you just do the top curve minus the bottom curve. So when we revolve it around this axis, this right here is the little radius, and that little radius is the cubic function, the top curve, minus the bottom curve, which is -1. The big radius, which is this distance, call that capital R, right there, is the top curve, 3x minus plus 1, minus the bottom curve. And as long as you do the top curve minus the bottom curve, you're gonna get it. Now I can generate this. You know that somewhere over here these curves intersect, and we'll call this B, and they do intersect at 0. So if I'm finding the volume, I'm going to do the integral from 0 to b of pi times the big radius squared minus pi times the little radius squared. And I know you can simplify that. If I go through and I show you the solution on this, I know that they're going through and they did plus and they did plus here, so they turn these double negatives. Did I write that equation wrong? Oh yeah, this is 3 plus 1 here. This is cubed, and this is plus 1 here. But they're gonna do some simplification, and then they found where these two things intersect, whatever that value is. Remember, when you're finding intersection values, take it out to maybe 8 decimal places, because if you use this bound to only 3 decimal places, you will create a rounding error in the answer, and so that's a little bit of an issue. So when you think about how this looks, when I start to pull this away, you can see those disks that are generated as we start revolving this. As I start revolving this, as I make this slider go to 0 and then I start revolving it, you can see those disks, and you can see the three-dimensional shape that is generated. Hopefully that helps, and good luck.